Good afternoon, everyone. Today we are meeting for the second lecture of the current series. In the today's class, we are going to start with the topic which is propagation of a plane electromagnetic wave in a homogeneous and isotropic medium. In the previous lecture, I have explained that a medium in which the properties are not changing with direction is known as an isotropic medium. The homogeneous medium is one in which the electromagnetic properties are same at all the points. So today we are going to understand that how a plane electromagnetic wave travels through a medium and with what velocity it propagates. So we will start with the Maxwell equations that we have written in the previous class. The Maxwell equations for a homogeneous isotropic medium are written as divergence E is equal to rho by epsilon. This is first equation. We have written these equations in the previous class. The second equation is divergence H is equal to 0. The third equation is minus mu del H by del T, and the fourth equation is curl H is equal to J, which can be written as sigma into E plus epsilon del E divided by del T. So this is equation number 3 and this is equation number 4. These equations marked as 1 to 4 are Maxwell field equations for a homogeneous and isotropic medium. In these equations, we have two terms. One is this mu, another is this epsilon, which we can expand as, where mu is written as mu 0, mu r, and this epsilon is written as epsilon 0, epsilon r. What we can do, we can restrict ourselves to a medium which is we call as free space. So when we say free space, it means the same as vacuum. So if you have a medium which is free space and vacuum, then these relative properties, which is mu r and epsilon r, will be 1. So this mu r and epsilon r will be 1. Accordingly, this mu is now equal to mu 0 and this epsilon is now equal to epsilon 0. Further, the medium that we are considering is free space. So we assume that there is no free charge density. There is no free charge density. No free charge density implies the value of rho becomes 0. And if we say that it is free space, then it is also non-conducting. So a non-conducting medium have a electrical conductivity which is 0. So we have made certain restrictions for our medium. For free space, we have taken mu is equal to mu 0, epsilon is equal to epsilon 0 as the relative permeability, and relative permittivity is 1. Further, the medium contains no free charge density and hence rho equals to 0. And if we say that it is non-conducting, then sigma is also 0. So we will make certain changes, these changes in our Maxwell equations. So making the changes in Maxwell equations. So I will make the corrections on the next slide. So the first equation, which is divergence E is equal to rho by epsilon, that is now left as divergence E equals to 0 as the value of rho is 0. So this is my equation number 5 now. The sixth equation is divergence H equals to 0. This is my equation number 6. The third Maxwell equation is now left with curl of E is equal to minus mu 0 del H by del T. And similarly, the last equation is now left as curl H is equal to epsilon 0 del E by del T. So these are the Maxwell equations for free space. So now I can write that these four equations belongs to free space. So the previous equations that we have written in the last class as well as in the today's class in the last slide, those equations are in the general form. Now we have made it specific for free space or vacuum. Now let us proceed with certain mathematics. I can take the curl of equation 7 on both sides. So taking the curl of equation 7 on both sides. So this will be left as curl E is equal to minus mu 0 del by del T of curl H. The equation on the left hand side, which is curl E, can now be expanded using the identity, which is gradient divergence E minus del square E. We can use the value of curl H from equation number 8, which is epsilon 0 del E by del T. So this term, which is gradient divergence E, is 0. So we are left with del square E is equal to minus mu 0 epsilon 0 del square E over del T square. So let me name this equation as equation number 9. We have already written the number till equation 8. So this is equation number 9. So similarly, proceeding in the same fashion, if we have taken the curl on equation 8, we would have got a similar equation. So I will not do that procedure again. I will simply write del square H is equal to mu 0 epsilon 0 del square H divided by del T square. This negative sign in equation 8 is not there as it is cancelled on both the terms. So this is plus. Similarly, this is our equation number 10. So these equations are very important, as on the left hand side we have the space derivative, second order space derivative, and on the right hand side we have second order time derivative. So this del square is nothing but Laplacian operator, which is del square by del x square plus del square by del y square plus del square by del z square. So it means on the left hand side we have space derivative and on the right hand side we have time derivative. So whenever the second order space derivative and second order time derivative are related, we say that these equations are equations 9 and 10 are similar to standard wave equations. Similar to standard wave equation. What is that standard wave equation? I will write in the next slide. So the standard wave equation is of the form second order space derivative. Any function which is f is given by 1 over v square del square f divided by del t square. So as you can see in this equation 11, on the left hand side we have space derivative and on the right hand side we have time derivative, and the term which is in the coefficient denotes 1 upon square of the velocity. So we can compare equation 9 and 10 with equation 11. So we will get that v square is 1 over epsilon 0 mu 0, or you can find out the v, it is 1 over under root of mu 0 and epsilon 0. So this is the velocity. Now the question comes, it is the velocity of what kind of effect? So we say that the electric and magnetic effects, that is electric vector E and magnetic vector H, travels in a medium, and it travels with a velocity which is given by equation number 11. So I will write what I have said, that equation 9 and 10 represent the general equation for the propagation of electric vector E, magnetic vector H in a free space. You can also call it E and H. If you want to write it in single word, you can write electromagnetic. Propagation of electromagnetic effect in free space or vacuum with a velocity given by equation 11. So this equation 11 can be expanded in terms of mu and epsilon. The value of mu 0 is 4 pi into 10 raised to power minus 7, and the value of epsilon 0 is 8.85 into 10 raised to power minus 12. When we use these values in the equation, the velocity can be solved and it will come out to be of the order of 3 into 10 raised to power 8 meter per second. So this is the velocity of electromagnetic wave when it travels through the medium, through the free space. So we see that this is nothing but the velocity of light. So it was concluded that the electromagnetic effects travel in a medium with a velocity of light. So light is a special case of electromagnetic wave. So what we can do, we can restrict the equations number 9 and 10 to a one direction only. So if we say that the propagation of EM wave in free space is restricted only to y direction. So if we have restricted the propagation of EM wave only along y direction, equation number 9 and 10 is modified. So it is modified in a way that on the left hand side the space derivative del by del x and del by del z reduces to 0. So I will do that correction in the next page. So equation number 9 and 10 are modified as del square E divided by del y square is equal to mu 0 epsilon 0 del square E divided by del t square. Similarly, del square H divided by del y square is mu 0 epsilon 0 del square H divided by del t square. So these equations, I will call them equation number 13 and equation number 14. These equations are representing the plane progressive harmonic wave for this electric vector E and magnetic vector H along y direction with a velocity which is given by equation number 12. So I will write it down that equations 13 and 14 represents a plane progressive harmonic wave. For electric vector E and magnetic vector H in positive y direction with a velocity given by 3 into 10 raised to power 8 meter per second. So this velocity comes from the expression that we have written in the previous page, that this velocity is given by 1 over square root of mu 0 and epsilon 0. So this is a very important result in the electromagnetic theory, that the electromagnetic effects travel in a medium, travel in vacuum with a velocity which is equal to the velocity of light. So hence it was concluded that light is a special case of electromagnetic wave. So we will write the conclusions. So the following conclusions can be drawn out from the analysis, that all the electromagnetic effects propagates in vacuum as a wave. I should write which are known as electromagnetic waves. So whenever we say that there is an electromagnetic wave, we mean to say that are electric and magnetic effects that are propagating in that medium. The velocity of the wave is given by 0 epsilon 0, which can be solved as the value of mu and epsilon are known. The value of mu 0 is 4 pi into 10 raised to power minus 7. The value of epsilon 0 is 8.85 into 10 raised to power minus 12. So upon solving, this velocity comes out to be close to 3 into 10 raised to power 8 meter per second. So it can be concluded that light waves are a special case of electromagnetic waves. So this was the theoretical result that we have got. So this theoretical result has later proved experimentally. So Maxwell theoretical prediction regarding EM wave were proved experimentally. By Hertz. Hertz proved that EM wave have transverse nature and they travel with a speed which is known 3 into 10 raised to power 8 meter per second, and these waves shows the phenomena like reflection, refraction, like visible light. So this is a very important result of electromagnetic theory, that light is a special case of electromagnetic wave, and all these electromagnetic effects travel in vacuum with a speed which is given by 3 into 10 raised to power 8 meter per second. So the next important thing that we can discuss is transverse nature of electromagnetic wave. So when we say that the electromagnetic wave are transverse, we mean to say that the electric affects the magnetic affects the electric, we can say that the velocity of the EM wave and the electric vector E and the magnetic vector H, all three are mutually perpendicular to each other. So using this mathematics over the equations that we have done today, we can prove that the electric field E0 can be written as Similarly, the magnetic vector H can be written as from these two equations, we can say that this electric vector is perpendicular to the plane of H and J. J is the direction of propagation. So if we have a wave which is propagating in y direction, so let us say that the wave is propagating in this direction, which is y. This is y direction. The wave is propagating in this direction. Then this electric vector has to be perpendicular to J and H. That is, electric vector is perpendicular to direction of propagation as well as magnetic vector. Similarly, the magnetic vector is perpendicular to J and E. It means that all the three vectors E, H and J are perpendicular to each other. So along this X direction, we can have this electric vector, and along this Z direction, we have this magnetic vector. So this E cross J will give you H, and this J cross H will give you. So along with this direction and with the help of these two equations, we can understand the transverse nature of EM wave. So let me call this as equation number 1 and equation number 2. So I can write that from equation 1, we can say that electric vector is perpendicular to J, direction of propagation, and H0, which is magnetic vector. Similarly, from equation 2, we can say that H0 is perpendicular to E0 and J. So hence from this equation 1 and 2, we can say that all the three vectors E, J and H are mutually perpendicular to each other. I will write that over the next page. So hence it can be concluded all the three vectors, which are E, H and J, are mutually perpendicular to each other. So this result, that E is perpendicular to V and is perpendicular to B, that all these three vectors E, V and B, you can also write it as H. There is no problem with that. This B or H, both are the same. So this E, V and H all are mutually perpendicular. This result is called transverse nature of electromagnetic wave. So from the elementary mathematics, it can be proved that wave. So this nature, that E is perpendicular to V is perpendicular to B, is known as transverse nature of EM wave. Further, from the equation that we have derived in the previous page, that E0 is given by H0 cross J divided by epsilon 0 into V0. This equation can be modified as we can expand the numerator and use the value of V0, velocity of EM wave, from the previous expressions, we will get upon solving this equation, we will get so the equation in the equation 1, the left hand side has the dimension of resistance, and hence it is known as characteristic impedance of free space. As we know the value of mu 0 and epsilon 0, we can calculate the value of E and H. So the ratio E by H will come out to be 377 ohm. So this ratio E by H, which is 377 ohm, is known as characteristic impedance of free space. We denote it with Z, so we say that characteristic impedance Z is equal to 377 ohm. So with this, we will end our discussion today, and we will meet in the next class for the next topic. Thank you.